Good morning, everyone. Today's session is on high-resolution satellite imagery, HRSI, and its applications in land use, planning, and governance. We'll explore what HRSI is, how it's collected, and the many ways it's being used to solve real-world problems.
Let's discuss what is remote sensing. Remote sensing means collecting information about the Earth's surface without direct contact, using satellites, aircrafts, or drones. GIS, or Geographic Information System, is a digital system that stores, analyzes, and maps this data. Together, they help us monitor land, water, forests, and even cities for better planning and decision-making.
Now that we know what remote sensing is, let's look at how the data is collected. Remote sensing uses different platforms. Think of them as the vehicles or tools that carry sensors to capture information. There are 4 main platforms, each with its own strengths. Satellites cover very large areas from space, giving us a big picture view of the Earth. Aircraft fly at lower altitudes and are used for detailed aerial photography. UAVs and drones, highly flexible, cost-effective, and provide very high-resolution data for smaller areas. Ground sensors, placed directly on the Earth's surface, giving the most detailed and accurate data, but only for specific sites. So each platform has its strengths depending on the scale and resolution we need, whether it's a global view from satellites or a detailed site survey using drones or ground sensors.
This slide raises a question. Where does the data come from? The main sources include satellite imagery like Landsat and Sentinel-2, aerial photography for detailed mapping, UAV data for very high resolution, and GIS databases such as parcel maps, zoning layers, and infrastructure data sets. These combine to create a complete picture of land use. High-resolution satellite imagery, or HRSI, means each pixel represents a very small area, often 30 centimeters to 1 meter. This allows us to identify buildings, vehicles, and even trees. Free examples include Sentinel-2, Landsat, and Spot data. Such imagery forms the backbone of urban planning, monitoring, and environmental management. Some open-access, free, high-resolution data examples include NAIP, 0.6 to 1 meter resolution, or USA only, Spot 6-7, sample scenes, 1.5 meter resolution, Airbus sample portal. Open aerial map, various resolutions from community uploads. One of the most important tasks in remote sensing is classification, which means categorizing pixels or objects in satellite imagery into meaningful land cover types, such as water, forest, agriculture, or urban areas. There are different approaches to classification. The simplest is unsupervised classification. Here, the computer automatically groups pixels based on their spectral similarity. For example, clusters of green pixels may be grouped as vegetation. But since it works without prior knowledge, the analyst must later assign real-world labels to these groups. The second approach is supervised classification. In this method, we provide training data, that is, we tell the software what each class looks like by selecting sample areas, such as patches of water, forest, or settlements. Then the algorithm applies this knowledge across the entire image, producing much more reliable results. Beyond these basics, advanced techniques provide even greater accuracy. Object-based image analysis, or OBIA, first segments the image into objects instead of individual pixels. This allows it to use not only color or spectral values, but also texture, shape, and spatial context. For example, a road can be identified not only by its color, but also by its linear shape and pattern. Modern remote sensing also uses machine learning classifiers like random forest or support vector machines. These algorithms can handle complex data sets and multiple variables, producing high-accuracy maps. For example, random forest can classify different types of crops or roof materials in urban areas. In summary, classification techniques transform raw satellite imagery into practical maps, enabling us to see not just pixels, but meaningful land categories. These maps are essential for urban planning, environmental monitoring, and policy decisions. After classification, the next step in remote sensing is object detection. Unlike classification, which broadly divides land into categories like forest or urban, object detection focuses on identifying and locating specific features, such as buildings, roads, vehicles, ships, or even small tanks and trees.
Automated methods, on the other hand, use algorithms and software to speed up detection. Feature-based detection relies on edges and shapes, like extracting roads using linear features. Machine learning techniques go further by training models to detect objects based on size, shape, and texture, such as identifying different roof types in a city. With the rise of AI, deep learning methods using convolutional neural networks, or CNNs, have become very powerful. They can automatically detect complex objects like ships in harbors, vehicles in traffic, or even new constructions in urban areas. Another important application is change detection. By comparing images from different dates, we can see what has changed over time. For example, we can detect new buildings, disappearing wetlands, or expanding urban areas. This is especially useful for monitoring encroachment, flood damage, or illegal land use. To sum up, object detection turns high-resolution satellite imagery into actionable intelligence. It helps planners, engineers, and policymakers pinpoint exactly where changes are happening and what kind of features exist on the ground, making governments smarter and more responsive.
This slide shows two examples of high-resolution satellite data and how they are used in practice. On the left, we see an orthophoto generated from a drone survey. Orthophotos are geometrically corrected images, meaning they are aligned to the Earth's surface and can be used like a map. They provide very fine detail, which we can clearly see roads, houses, and even individual features within a city block. On the right, we have an Esri Maxar streamed layer, which can be accessed through QGIS or ArcGIS software. Maxar Imagery provides high-resolution satellite views, allowing planners and researchers to zoom into urban or rural areas and analyze land use patterns, encroachments, or development changes. Together, these examples highlight the two key sources of high-resolution data: UAV or drone-based imagery for localized, highly detailed surveys, and commercial satellite imagery like Maxar for larger coverage and integration into GIS platforms.
His slide highlights some important examples of free satellite datasets that are widely used in research, planning, and governance. The first is Sentinel-2, developed by the European Space Agency. It provides 10-meter resolution and 13 spectral bands, capturing data every 5 days. Sentinel-2 is especially useful for land cover mapping, agriculture, vegetation monitoring, and flood mapping. Data can be accessed freely from the Copernicus Open Hub, or EO browser. The second example is AW3D, a global digital surface model developed by JAXA. The free AW3D30 dataset offers 30-meter resolution with worldwide coverage. It is particularly valuable for terrain analysis, flood modeling, orthorectification, and 3D visualization of landscapes. The third example is the well-known Landsat program, a joint effort by USGS and NASA. Landsat provides 30-meter multispectral and 15-meter panchromatic data, with an archive going back to the 1980s. This makes it extremely powerful for studying long-term environmental changes such as deforestation, urban growth, or river erosion. The data is freely available through the USGS Earth Explorer. Together, these datasets, Sentinel-2 for frequent and detailed observations, AW3D for terrain and elevation, and Landsat for historical records, form the foundation for monitoring and managing natural resources and urban development.
This slide is a really clear demonstration of why spatial resolution matters in remote sensing. Here, we see the same area captured on the same date, 3rd August 2021, by 3 different satellites. Sentinel-3, 300-meter resolution. On the left, the image is very coarse. Each pixel represents 300 meters on the ground, so the features are blurred. You can see the general shape of the water body, but no fine details. Landsat 8, 30-meter resolution. In the middle, the clarity improves a lot. Each pixel is 30 meters, so you start seeing land-water boundaries more sharply and can identify some patterns in surrounding land use. Sentinel-2, 10-meter resolution. On the right, the detail is much higher. Each pixel is just 10 meters, so you can clearly distinguish coastlines, small islands, and even different land covers. So, the smaller the pixel size, the higher the spatial resolution, and the more detail we can extract. Sentinel-2 allows us to see fine-scale features, which is essential for urban studies, agriculture monitoring, and environmental analysis.
Now, let's wrap up. This slide highlights the key portals where you can easily access optical, radar, and elevation datasets, and all are completely free of cost. To conclude, high-resolution satellite imagery is more than just pictures from space. It is a decision-making tool for government, science, and society, enabling better planning, sustainable development, and improved governance. Thank you for being part of this session.